Okay, so now we're going to look at derivatives of polynomials. So we'll break it down step by step, and our main goals today is to understand how to use the power rule, the constant multiple rule, and how to handle negative and fractional exponents when taking derivatives. So we'll also be touching up on calculating higher order derivatives. So let's start with the foundation, the power rule. This is like your go-to rule for differentiating terms that look like x squared, and then where n can become any real number. So I'll touch up on that in slides. And then another one is that understand how to use the constant multiple rule. And then we're going to look at as well as how to calculate negative exponents, or how to calculate derivatives with negative and fractional exponents. And then lastly, we'll just look at calculating higher order derivatives. Okay, so now to dive into power rules. So what power rules do is that it helps us find the derivative of functions that involve exponents. So the main formula we use here is d over dx, x at n is equal to nx to the exponent of n minus 1. So I know this looks a little bit confusing, but it's really not too hard. So the d over dx just means we're finding the derivative with respect to x. And when we have a function like x raised to the power of n, so x to the n, the power rule tells us to do two things. So bring the exponent down and multiply by the x, so the n comes to the front. And then subtract 1 from the original exponent so that the new exponent becomes n minus 1. So now we'll look at some examples just to make this more clear. So imagine we have the function, we have the function x to the power of 5 using our power rule formula. So d over dx to the power of 5 would give us 5x to the power of 5 minus 1, right? So then that would just become, when we bring the 5 down and subtract the 1, it would just give us 5x over 4. Right, that one's pretty simple, that one's pretty easy. Now, what if our exponent is a decimal? So now when we have x to the power of 2.5, the rule will still work. When we have d over dx, with x to the power of 2.5, it would just be equal 2.5x to the power of 2.5 minus 1, which would become 2.5x to the power of 1.5, right? So it's generally so easy. You just you would make it simpler, you would multiply the coefficient with the exponent, and then you would subtract 1 from the numerator. So, or sorry, you wouldn't multiply the exponents. You would make it that exponent. So if we have x5, we would just make it 5x, and then we would always just subtract that by 1. It becomes very simple. So now again, when we have x to the power of -3, we would bring the -3 to the front, make it our coefficient, and then we would subtract it by 1. Now remember, it's negative, so -3 minus 1. Lots of people think, oh yeah, it turns into -2. It actually turns into -4. I know subtracting negatives everybody knows, but people get mixed up in the exponents because there's already so much to think about. So yeah, people can get mixed up in the exponents here. So then it would become -3x to the power of -4. And then lastly, when we have x to the power of 5 over 2, this is with a fraction now, it's nothing different. You would bring the fraction to the front, it would become our coefficient. So then 5 over 2x, and then you would just subtract it by 1. So 5 over 2 minus 1 minus 1 would become 3 over 2. So then 5 over 2x to the power of 3 over 2. So it's very, very simple. You get it within it's two steps. It's a two-step process, and it's very easy to do. All you do is bring exponents to the front and then reduce the exponent by 1. There should be no issues solving it here. Okay, so now we're in the constant multiple rule. Sounds a bit fancy, but it's very, very straightforward, just like our power rule. Imagine now we have a function and we're multiplying it by a constant number. So the rule tells us how to find the derivative of the whole thing. So formula is d over dx with cx to the power of n, and then that equals c times nx to the power of n minus 1. So again, looks very complicated. It isn't too complicated. What does this mean? Well, c is just a constant number, like 2, 5, whatever, -3, and then, or it can even be a fraction, and then x is our variable, as we know, and n is the exponent. That's what all of them represent. It's very simple. So the rule basically says that you can keep this constant c just staying there, and then you multiply it by the original exponent n, and then finally you subtract by 1 in your original exponent to get the new exponent. So in example 1, we have 5x to the power of 3, and c is 5, our constant, and n is 3, our exponent. So now we follow the rule. 5 times 3, x to the power of 3 minus 1, which will become x to the power of 2. This simplifies to 15x squared. We just multiplied by our constant, and we multiplied 5 by 3, and reduce the exponent from 3 to 2. It's that simple. It's just like the power rule, just like with maybe another step. So again, when we look at example 2, we see 3x to the power of 3.5. Our constant c is 3, and our exponent n is 3.5. So now, again, we would just do 3 times 3.5x, and then our exponent would be 3.5 minus 1, which would become 2.5. And this gives us a total of 10.5x to the power of 2.5. And then, so yeah, it's basically doing the power rule again, except you're just multiplying with the coefficient, with the constant. All right, so now we look again at 7x to the power of -3. But now here's a twist. We have a negative exponent, okay? So c here is 7 and n is -3. So what we do use our rule, which is 7 times -3x, and then -3 minus 1. So then this becomes -21x minus 4. Or sorry, -21x to the power of -4. And notice how subtracting from 1 from -3 results in -4. It goes like it seems like it's going up, but it's not, right? And then fractions as exponents. So when we have something like 6x to the power of 3 over 2, our constant is 6, and then our n is 3 over 2. So now when we apply the rule, we have 6 times 3 over 2 to the power of 3 over 2 minus 1. That becomes 1/2, right? So now firstly, 6 times 3 over 2 is 9. It's like 6 times 1.5. And then 1.5 or 3 over 2 minus 1 is 1/2. So the result is 9x to the power of 1/2. So generally, just to wrap it up again, the constant multiple rule is all about multiplying your constant by the exponent and then reducing the exponent by 1. It's just a basic fundamental of complex functions. So again, it looked hard, just like power rule. They both look hard, but from this equation, but it's really more simpler than you think. Okay, now for multi-term polynomials, we'll start off with a very important rule. The derivative of any constant is always 0. So a constant is just a number without any variables attached. So for example, if we have the function y equals 5, derivative is written as dy over dx is 0, right? This is because a constant value doesn't change. So its rate of change, its derivative, the rate of change, is 0. So the rule is d over dx is a constant which equals 0, right? And now we include our power rule as well. And we when we include power rule, we saw power rule in the previous slide. So now when we differentiate a polynomial, we'll look at this equation. So we'll look at y equals 6x to the power 5 minus 3x power 3 plus 4x squared minus x. And then I'll show you how this became 0. So to find the derivative, right? So generally this was minus x plus 5. So to find the derivative, it would be dy over dx. So then we would apply the power rule. So for 6x to the power 5 using power rule, we multiply 6 by 5 and reduce the exponent by 1. So 6 times 5x to the power of 5 minus 1, that equals 30x4. Okay, now we'll do the same for the others. Negative 3x to the power of 3, multiply negative 3 by 3, reduce the exponent by 1. We get negative 3 times 3x to the power of 3 minus 1. That becomes negative 9x squared. Again, for 4x squared, we would do 4 times 2. 4 times 2 to the power of 2 minus 1. That becomes 8x to the just to the power of 1, or just 8x. So yeah, this is pretty simple, right? We're just using power rule here. And then for negative x, we're going to do like it's just the same as negative 1x to the power of 1. We're going to multiply negative 1 by 1 and reduce exponent by 1. So negative 1 times 1x to the power of 1 minus 1, that becomes negative 1x to the power of 0. Okay, so this is very important here. When any non-zero number is raised to the power of 0, it becomes 1. And negative 1 times 1 is negative 1. So for plus 8, this is a constant. It doesn't have any variables. So the derivative is just 0. It's just a flat 0, right? Whereas the variable that has a single term would just turn into 1, right? Or, well, not a single term, sorry. For one that has an exponent to 1, that turns into a 0. Okay, so now we just add the derivatives up of each term, 30x4 minus 9x squared plus 8x minus 1 plus 0. And then the final derivative is the same thing. We just take out the 0. And this is our full derivative. And we don't have to write x to the power 0. I just wrote it to make it easier to understand and make it more simpler for you guys. And then yeah, that's for that part. And then for example 2, it's the same thing. I'm just giving you guys another example. So negative 5x squared minus 3x to the power of 5 plus 2x4 minus 7x, and then what's supposed to be minus 10 turned into 0. So again, we just use power rule, and then at the end we would rearrange. So for negative 5x to squared, we would multiply negative 5 by 2 and reduce the exponent by 1. This would become negative 10x. Then, sorry. And then for minus 3x to the power of 5, we would multiply negative 3 by 5, get 5x to 5 minus 1 to the power of 5 minus 1. This become negative 15x to the power of 4. And then for 2x to the power of 4, we'd multiply 2 times 4. That gives us 8. And then we also have 4. We also had 4x to the power of 4 minus 1. So then it gives us a total of 8x to the power of 3. And then lastly, this is pretty important. For negative 7x, this is like negative 7x to the power of 1. So we multiply negative 7 by 1. But the 1x is to raise to 1 minus 1, which is 0. Again, this is the most hardest part of it all. After this, it becomes easy. And then since x to the power of 0 is just 1, this becomes negative 7 times 1. And this equals negative 7. So it's very simple. There is no constant term here, or there was earlier, minus 10. We always just turn it into 0. And there's also one little thing I forgot to mention. dy over dx is actually the slope in y equals mx plus c. So the m that we used to see in grade 9, the slope, that's the same thing. It's just we're rewriting it. It's like how we went from grade 10 to 11, we changed y to f at x. It's the exact same thing. So dy over dx turned into m. So yeah, this is what when we find derivative, we say we found the rate of change. Rate of change was slope, right? So this is all the same thing, just in calculus. All right, now when we look at negative exponents, we see that so we look over here where our example is 1 over x3 equals x to the power of negative 3, right? And this is simply because when we have an exponent in the denominator, the numerator, it can change its sign. So whenever we switch it, it changes the sign. So the variable has to be in the numerator usually, and then we can change the sign. So if it's x to the power of -3, we can just change it to put in the denominator and make it 1 over x to the power of 3. So in this case, we're trying to find the derivative, right? And when we look at this function, for example, so we have y equals 5 over x to the power of 3 plus 3x to the power of 2 plus 3 over x to the power of 2 minus 4 over x plus 1 over 2. Okay, so we would first bring all these exponents to the top, right, to find the derivative, because all variables have to be in the numerator when we have to find for derivative, right? So then what we would do is that we'd bring it to the top. It would become 5x to the power of -3 plus 3x to the power of -2 minus 4x to the power of -1 plus 1/2. And then that just becomes 0 because it's a constant term, right, when we're trying to find the derivative, right? So now when we use power rule we would just multiply the exponent by the coefficient. So -3 times 5 equals -15x to the power of -4, because -3 minus 1 is -4. So now we have -15x to the power of -4. Then -2 times 3, that's -6. And then -2 minus 1 is -3. So then minus 6x to the power of -3. And then lastly, -4 times -1 is plus 4x to the power of -2. And then 1 over 2 cancels out because it becomes a 0. It's a constant term. And that's our answer for finding derivative. It's very simple. And then if you want to do an optional step to make your exponents positive, sometimes it's asked in the question, sometimes it's not. If it is, you would just change your exponents and bring them back to the bottom. So then -15 over x to the power of 4 minus 6 over x to the power of 3 plus 4 over x to the power of 2. That's all. Now we have higher order derivatives. So when we were looking at derivatives, we were always solving for the first derivative, dy over dx, right? But there's actually higher order derivatives as well, such as d squared y over dx squared, or d to the power of 3 y to the power over dy to the power of 3, and then d4 y to the power of dy over to the power of 4. So why we do this? So we find the change of the rate of change, and this shows us concavity and so on. So then f at x equals f1 at x, then that becomes to f2 at a second derivative, raised to the second derivative, then to the third derivative, then to the fourth derivative. So we'll look at our first example here. So f at x equals 8x to the power of 5 minus 3x to the power of 2. When we do, all we do is power rule just to find our derivatives, right? So 5 times 8, 40, 5 minus 4, 5 minus 1 is 4, that's 40x 4, 2 times 3, 6, well, 2 times -3, 6, and then 2 minus 1 is 1, so we have minus 6x. Then we have 160x to the power of 3 when we do 4 times 40, and then 4 minus 1, and then minus 6, but this becomes 0 because when we do x, because this is x to the 1, right? But when it becomes x to the 0, it's just going to become 1. So then that's just a constant term, and constant terms always get canceled out. So now we have a constant term, it's a 0. So now we're only left with a single term. Now f to the third derivative is 480x squared, and f to the fourth derivative is 960x, right? When you just keep doing the power rule. And then we can also do it with our negative exponents and when we have fractional exponents as well. So when we do it like that, then it would be f at x equals, or f at x equals 3 over x to the power of 3 minus 2x to the power of 7 over 2. So as we knew with the negative exponents, we would bring it back to the top. It would become 3x to the power of -3 minus 2x to the power of 7 over 2, because remember, all the variables have to be in the numerator. Okay, it's a rule for exponents. It's a rule for the negative exponents. So now when you raise it to the first derivative, again, all we're doing is just solving the power rule. So -3 times 3 is -9, and then -3 minus 1 is -4. Same thing, minus 7x. So then it would become 7 over 2 times -2, that's -7. And then 7 over 2 minus 1, that's 5 over 2. So then we have -7x over 5 over 2. When we do the same thing, we would get 36x to the power of -5 minus 17.5x to the power of 3 over 2. And then lastly, when we have the fourth derivative, we would do -5 times 36, we get -180. X to the power of -6 is -5 minus 1 is -6. And then minus 3 over 2 times 17.5, we get -17.5, and then we get -26.25x to the power of 1 over 2, since 3 over 2 is 1 over 2 when you subtract it by 1. So yeah, that's generally, like, I think the main rule here isn't, well, when we remember the negative exponents in this case, the main thing about derivatives is just you keep using the power rule continuously to find the changes of rate of change and to find the concavity patterns.
Okay, lastly, we'll just talk about some final mistakes that people make during this lesson and rules that we have to follow when we're going into this lesson. So first things first, remember mistake number 1, make sure to expand before taking on a derivative. So don't use chain rule when we have an unexpanded expression. For something like, let's say, bracket 2x plus 5 squared, the smart move is to expand it first. So we can't just go straight to using power rule or using chain rule and say like, oh yeah, 2 times 2x and then becomes 2, and then this becomes -1. No, we cannot do that, right? We'd have to expand it, and then we can use power rule. So then when we expand, this would become 4x squared plus 20x plus 25. And then when we use power rule, this would minus y1. This would multiply 8x. And then this would just become 0 because x to the power of 0 is just no variable. And then we have plus 20 and then plus 25. And then if we were to do another step, then we would cancel out the 20. Otherwise, now we wouldn't cancel out the 20. Since we are doing another step, we can cancel out the 25, right? Moves from right to left because our variable, right? And then when we treat c as a constant, y equals 2x squared plus c. If we're treating it as a constant, then it would become 0. We should always remember that. It would become just 4x plus 1, right? And that's also pretty simple to remember because can add an extra 1x, right? For c if it was just a variable. Like you can't just pretend it's a variable. So then now we also have rules here. So rule 1 is very important. The derivative of any constant is 0. So d at c over d at x equals, for example, d at 5 over d at x, which equals 0. And this is showing where c is constant. So the rate of change, the derivative, is 0, right? The constants are always 0. And because they're just, you can't treat them as a variable. Rule number 2 is about variables. So when you differentiate a variable with respect to itself, you get 1. So d at a over d at x equals 1, where a is a variable, right? And then finally, rule number 3, make sure your variable is in the numerator before you differentiate. So when we were dealing with the negative exponents, 5 over x to the power of 3, we'd rewrite it as 5x to the power of negative 3. And this form makes it easier to apply the power rule for differentiation. And that's the only way we could solve for derivatives. If we wanted to expand it into derivatives, we'd always have to bring the exponent to the top. That's a big, big rule to remember. And then power rule, of course. And then this unit, or this lesson and this unit become very easy once you know those two.